Hi, my name is Pearl. I'm an application scientist here at Micromeritics. Today we'll go over some basics of physisorption theory. So what is physisorption? Physisorption is short for physical absorption, and it is non-selective adhesion of gas molecule, the adsorbate, to sample, the adsorbent. It is driven by the van der Waals forces, and it happens when the heat of adsorption is greater than the heat of vaporization. Even though physisorption is non-selective, meaning there is no such thing as an active site as seen in chemisorption, it is affected by temperature, pressure, and also the surface structure. Usually, a physisorption analysis is performed at cryogenic temperatures and in liquid nitrogen or liquid argon. And the common adsorptive gases include nitrogen, krypton, carbon dioxide, and argon. We have a diagram on the right to help us understand how the surface structure affects the order of adsorption. Even though it is non-selective, if the gas molecule is exposed to more surface, a gas molecule will preferably adsorb first to that surface structure. So the D molecule will adsorb first to the site where there's more access to the surface, followed by the B molecule, and then E molecule on the flat surface, followed by the A molecule on the protruding surface. And finally, we have the C molecule adsorbing after the first layer is completed as a second layer. Here is a diagram that depicts the order of adsorption as a function of increasing pressure. The pressures are expressed in the relative pressure, which is the absolute pressure divided by the saturation pressure of the adsorptive gas. And at the low pressure region, the gas molecules adsorb onto the isolated sites at around 10 to the minus 3 relative pressure. And eventually it forms a single layer of molecule onto the surface at around 0.1 relative pressure. And then it moves on to building the multilayer at around 0.3. And as the pressure increases to near saturation pressure, we assume that all pores are filled. Here is the basic schematic of the static manometric gas adsorption instrument. The instrument is connected to the gas inlet, the vacuum pump, a sample tube which is immersed in a constant temperature bath, and all these components are separated by pneumatic valves, and then the pressure of the system is measured with the pressure transducers. When an analysis started, first, the sample holder is evacuated to be under a good vacuum, and then the sample tube is immersed in a constant temperature bath, typically liquid nitrogen. Next, we dose the sample holder with a known amount of the adsorptive gas, and then the pressure falls as the gas molecules or atoms are adsorbing onto the surface, and we wait until it reaches equilibrium to take the data point. Some additional successive dosing may be needed depending on how much the sample absorbs, and finally, we increase and decrease the pressure incrementally to collect an isotherm. Here is what the flex schematic looks like. So it follows a basic schematic of static manometric instrument with up to 3 analysis ports and the P0 tube and different gas inlets and vacuum pump, all separated by pneumatic valves. We have the pressure transducers dedicated to each sample tube and P0 tube, as well as a pressure transducer and a vacuum gauge connected to the manifold. So what is being directly measured? We're simply measuring the pressure and the temperature of the system. So from the direct measurement of pressure and temperature, we calculate the quantity adsorbed using the ideal gas law. On top of the PV equals nRT, we have the term Z, which is for the compressibility factor, to account for the non-ideal gas behaviors in the cryogenic temperatures. The quantity of gas is calculated from knowing the pressure, volume, and temperature of the manifold. So first, we calculate the quantity of gas initially dosed into the manifold, and then after the valve is open to let the gas expand into the sample tube, the quantity of gas left in the manifold is calculated. The quantity dosed is the initial quantity of gas in the manifold minus the final quantity of gas left in the manifold after the gas is expanded into the sample tube. From this calculated quantity dosed, we subtract the amount of gas in the free space, which is measured, to obtain the quantity absorbed, and finally we normalize this per a gram of sample. The value of interest here is how much gas has been absorbed onto the sample, as known as the quantity absorbed at a given pressure. In this manner, we obtain the isotherm that typically looks like this, which is the plot of quantity absorbed on sample versus the relative pressure at a constant temperature. Different isotherm shapes are classified by the IUPAC. The most commonly seen isotherms are type 1, 2, and 4. First, the type 1 isotherms are the characteristics of the microporous materials. Type 2 is the non-porous or macroporous materials. And we see type 3 isotherm when the gas-to-gas interaction is greater than the gas-to-surface interaction. Type 4 is a characteristic of mesoporous materials. Type 5 is similar to type 3, except that the sample has some pores. So an example of this is the water absorption on a hydrophobic material with pores. And finally, we have type 6, which is for the materials with uniform surface. Here's a chart that nicely summarizes the pore classification. So when we say nanopores, it's any pores that are less than 100 nanometers in diameter. The micropores are any pores smaller than 2 nanometers in size. Mesopores ranges from 2 nanometers to 50 nanometers. And macropores are the pores greater than 50 nanometers in size. With gas absorption, we can characterize the pores up to 100 nanometers. And if the pore sizes are greater than 100 nanometers, we have to use other techniques such as mercury intrusion. So what information can we get from an isotherm? Typically, we get the surface area, pore size distribution, and pore volume using the methods that are listed on the right. We'll go over these methods that are most commonly used in detail in the next few slides. First, let's talk about the BET surface area. The pressure range that is commonly used for BET surface area is from 0.05 to 0.3 relative pressure, but of course this can vary depending on the sample. BET stands for Brunner, Emmett, and Teller, which are the names of the people who came up with this model. The BET model was essentially the extension of the Langmuir model. Langmuir was the first person to propose using the gas absorption to calculate the surface area of a material by knowing the volume of a single layer of molecule that is absorbed, which is known as the monolayer capacity. But Langmuir assumed that only monolayer happens at any given pressure, which is not the case in reality. So BET extended this model to account for multilayer absorption. For the data reduction, we're looking for the linear region after the knee, which is designated as a point B. And the point B is empirically determined to be where the monolayer completes and the multilayer absorption starts. This linear region was typically reported to be from 0.05 to 0.3 relative pressure range for type 2 and type 4 materials. So here are some assumptions of the BET model. We assume that there's multilayer absorption happening, and then the sample has non-porous and uniform surface. The interaction between the absorbed molecules is ignored. The heat of absorption for the first layer is higher than the successive layers. And finally, the heat of absorption for the second and beyond equals to heat of condensation. With these assumptions, we arrive at the BT equation on the right, where V sub A is the quantity absorbed at a given pressure, and V sub M is the quantity absorbed at monolayer, and P0 is the saturation pressure of the gas, and C is the empirical BT constant. By linearizing this BT equation, we can plot this as a linear plot to obtain the slope and the y-intercept. And from the slope and y-intercept, we can calculate the monolayer capacity and then the C constant. And knowing the monolayer capacity, we can calculate the BT surface area by converting that to the number of gas molecules and then multiplying that by the cross-sectional area of one adsorptive molecule. And then finally normalize that surface area per a gram of sample mass. To select the appropriate BT region, we need to find the linear region after the knee of the isotherm. And the relative pressure range can vary sample to sample significantly from the 0.05 to 0.3 relative pressure, especially when it comes to microporous samples. So to account for this, Rockwell et al. Came up with the criteria, and as long as a given set of data meets this criteria for BT calculations, we have a valid BT surface area. The BT fit should be linear. The C constant should be positive. The pressure range should be limited to where the n times 1 minus the relative pressure continuously increases with the relative pressure, and this is known as the Rockwell transform plot. The pressure corresponding to the monolayer capacity should be within the selected pressure range. And then the calculated value of the relative pressure corresponding to the monolayer capacity should not differ more than the 10% from the value that's measured. So we can calculate that relative pressure by the equation below, so 1 over the square root of C plus 1. So here's an example of the BT data reduction of a microporous sample on our MicroActive software. So the Rockwell criteria that were mentioned in the previous slide is all embedded on our software. So we see the Rockwell transform plot at the bottom left, the BT transform plot at the top left, and we see that the C constant is positive as well as the slope and the y-intercept, and we see the correlation coefficient greater than 0.999. So it's really easy to interactively do the data reduction on our software. So next, we'll talk about the T-plot. For a T-plot, we need data points in the multi-layer adsorption region, so that can really vary depending on the sample, but typically from around 0.1 to 0.7 relative pressure. So before we talk about the T-plot, let's talk about the T-curve first, which is used in the T-plot and then the BJH methods. The idea here is that as opposed to the monolayer, the multi-layer adsorption is less dependent on the surface structure, but more dependent on the equilibrium pressure and temperature. So the statistical thickness of the adsorbed multilayer can be calculated by dividing the quantity absorbed at a given pressure by the monolayer capacity, which calculates the average number of adsorbed layers, and multiplying this by S, which stands for the effective thickness of the monolayer of the adsorptive gas. So for example, the S is 0.354 nanometers for nitrogen. The T-plot method applies this concept of statistical multilayer thickness curve on experimental isotherms. It can evaluate the micropore or mesopore volumes and the corresponding external surface areas. For the T-plot method, we need two things. First, an experimental isotherm, and the reference isotherm, which is ideally obtained from non-porous version of the experimental sample that has the same sample or the surface chemistry. The T-plot graph plots the quantity absorbed V sub A against the T, the standard multilayer thickness, on the reference non-porous material at a corresponding relative pressure. For the data reduction, we select the linear region after the micropore filling and before the capillary condensation to obtain the micropore volume. And for mesopore volume, we can select the linear region after the capillary condensation. This method is regarded as oversimplification, not accounting for the special nature of the micropore filling, but it still serves as a good estimate of the presence of micropore in a sample. The advantage of this method is that we can collect the simple nitrogen analysis without the micropore analysis, collecting the very low pressure data, and still we can estimate the presence of the micropores. In most cases, the ideal non-porous version of an experimental sample is not available, so different thickness curves were developed for different materials. We have many different expressions of thickness equations, but the ones that are listed here are the most commonly used. So the Harkins-Ura is good for samples with micropores. Halsey is good to be used with mesoporous materials. The Broekhoff-de Boer can be applied to the broader range, the combined range used for Harkins-Ura and Halsey. And then lastly, the KJS curve was developed for the narrow mesopores, so it can be applied to 2 to 8 nanometers of thickness. So this is an example of the T-plot applied on an activated carbon sample. So the linear region after the micropore filling and before the capillary condensation is selected. And then we use the Harkins-Ura thickness curve, and we see that the micropore volume and external surface area are estimated. Next, we'll talk about the pore size distribution method called BJH. The pressure range it uses is from 0.1 relative pressure all the way up to near saturation pressure, and both absorption-desorption curves are used. BJH stands for the three people who came up with this model, Barrett, Joyner, and Helenda, and it is a good method for mesopore size distribution, ranging from 2 nanometers all the way up to 100 nanometers. To calculate the pore radius, it simply combines the Kelvin radius with the statistical thickness of the adsorbed layer at a corresponding relative pressure. So what is Kelvin radius? The equation is listed on the bottom left, where V is the volume of the condensed adsorptive, gamma is the surface tension of the liquid adsorbate, R sub kappa is the Kelvin radius, or the curvature radius of the meniscus, and theta is the contact angle between the liquid and then the pore wall, which is assumed to be 0, so the cosine theta in the equation dissolves to 1. It basically describes the change in radius of the liquid meniscus formed in the capillary or the pore as the vapor pressure of the liquid decreases over the meniscus. So basically, the BJH method treats both adsorption and desorption isotherm as the imaginary desorption isotherm, undergoing stepwise emptying of the pores as the pressure decreases. So the diagram on the right shows how it would look like. So the highlighted in yellow is the thickness on the surface at a given pressure, and the blue is the adsorbate liquid core remaining in the pore. At this particular pressure, the larger pore has already been emptied, and then the liquid core is slowly being evaporated. Since we know this particular relative pressure, we can calculate the thickness from the thickness equation and then the Kelvin radius of this meniscus. So these two combined gives us the pore radius. Here is how the BJH adsorption and desorption pore size distribution look like on our software. So if our isotherm, experimental isotherm, has a hysteresis, the BJH adsorption can characterize the pore cavity size, and the BJH desorption can characterize a pore opening. So in this example, we can see that the BJH adsorption gives a distribution with a larger sized cavity compared to the size of the opening of the pore shown in the BJH desorption. Next, we'll discuss the Horvath-Kawazoe method, which uses the micropore filling pressure region, usually below 0.1 relative pressure. The HK method is used to characterize the pores that are less than 2 nanometers in size. This was developed for molecular sieve carbons originally, so this model can be applied to the slit-shaped pores. This was the first method that accounted for the adsorbate-adsorbent interactions by implementing what's called the interaction parameters. And this method is based on the Everett and Powell's model that describes the potential energy of a single molecule between two parallel planes. The assumptions were that the pores are treated either completely full or completely empty at a given pressure, and the adsorbed phase behaves like two-dimensional ideal gas. And finally, the potential energy of the adsorbate along the pore walls is averaged. These assumptions can be questionable, but this method is still very widely used, and it gives a great estimate of the micropore size distribution of carbons. Here is the HK equation. So on the left, we have the change in free energy that depends on the relative pressure, which we're measuring. And all the other parameters are known depending on the adsorbate and adsorbent that are used for the experiment. So essentially, we're calculating for the L, the distance between the two nuclei of two layers, which is the pore width for the slit-shaped pores. Next, the cytofoley is an extension of the HK method to characterize the cylindrical pores below 2 nanometers, developed for zeolites. On top of the assumptions that were made for HK, it assumes that the pores are perfectly cylindrical with infinite length. And the equation is very similar, so we see the change in free energy on the left of the equal sign, which depends on the relative pressure, and the radius of the cylindrical micropore is calculated at a given pressure. Chang-Yang is the third extension of the HK model, developed to characterize the spherical pores for cavity-type zeolites like 13X. And on top of the assumptions made for the HK, it assumes that there's an exclusive interaction between the adsorptive molecules and the oxygen atom in the pores. And the pore wall is consisted of a single planar lattice. This model accounts for the nonlinearity of type 1 isotherm, which is a characteristic of the microporous materials with the Langmuir model. The equation is also similar, so we're calculating for the radius of the spherical pore at a given relative pressure. Here is how the HK model looks like on our software. So we can choose slit, cylinder, and sphere pore geometry depending on the material. And the interaction parameters can be selected based on which type of sample is used and which adsorptive gas is used. Next, let's take a look at Dubinin-Radushkevich method. Dubinin was the first person to define the pore ranges and classify them into micropores, mesopores, which was called transitional pores at first, and macropores. Dubinin and Radushkevich first came up with the method to characterize the micropore volume as well as its equivalent surface area in 1964. The relative pressure range used for this technique ranges from 10⁻⁴ to 0.1. Dubinin was the first person to identify the fact that layer-by-layer adsorption is not applicable for micropores, since their size is often in the order of 1 molecular size of adsorptive gas. Dubinin and Radushkevich developed an empirical equation to characterize the micropore volume and its equivalent surface area of microporous carbons, considering the volume-filling nature of micropore adsorption. Their theory incorporates the Polanyi's adsorption potential theory that describes the adsorption layer as a thick, compressed film of decreasing density with increasing distance from the surface, where the adsorption is driven from the long-range attractive forces coming from the solid surface. The adsorption potential is expressed as the universal gas constant R times the absolute temperature T times the natural log of reciprocal relative pressure, which equals to the change of Gibbs free energy. Dubinin-Radushkevich model is also available to apply to other microporous materials other than carbons. The Dubinin-R equation is highlighted in yellow, where W is the adsorbed amount at a relative pressure, W naught is the limiting micropore volume, E naught is the characteristic energy of the reference vapor, which is benzene. Beta is the affinity coefficient of the adsorptive gas that is used to collect the experimental isotherm, which is relative to the reference vapor. And finally, A is the adsorption potential. The A over beta times E naught is squared in the Dubinin-R equation, and this is the only change that is made for the Dubinin-Radushkevich equation to N, which can be user-defined to better fit the linear regression. The experimental isotherms can be plotted as a natural log of W against a square natural log of reciprocal relative pressure, as shown on the upper left graph. A linear regression analysis can be performed where the micropore volume and its equivalent surface area can be derived from the y-intercept of this straight line. Dubinin-R is frequently used with CO2 isotherms collected on the microporous carbons at 273 Kelvin, and this model is useful when it comes to the microporous carbons that are diffusion limited with a typical nitrogen analysis at 77 Kelvin. Here is an example of CO2 isotherm plotted as a straight line applying the Dubinin-R equation in the MicroActive software. Lastly, we'll talk about the NLDFT, which uses the pressure from the very low pressure region all the way up to the near saturation pressure. And it can characterize the pore size distribution from adsorption, desorption curves separately or combined. NLDFT stands for non-local density functional theory, and this method is used to characterize the micropore and mesopore size ranging from down to 0.3 nanometers to 50 nanometers depending on the adsorptive gas. And unlike the classical models that we have been discussing so far, the NLDFT takes the microscopic molecular approach in terms of the liquid density inside the pores. So on the right, we have a graph that plots the density of nitrogen and argon at different temperatures versus the diameter of the pores in nanometers. The most common analysis conditions is the nitrogen at 77 Kelvin, shown in green. And the gray dotted line is the bulk density of the liquid nitrogen that are used in the classical models for pore size calculations. We can immediately see that the density of the liquid adsorbate depends heavily on the size of the pores, being significantly lower than the bulk density under 10 nanometers of the pore size. So the NLDFT takes this fluid to solid interactions as well as the fluid to fluid interactions into account, treating the adsorbate fluid as inhomogeneous to simulate the density profile depending on the types of materials being analyzed, geometry of the pores, the adsorbate gas, and the temperature. More recent models called 2D NLDFT also takes the surface heterogeneity into account, and all the different models are available on our website. So let's take a look at the equation used for simulating and calculating for the density profile. The grand potential functional, called the omega, is the combined potential of the whole system, including the free energy functional, which is the fluid-fluid interaction, external potential, which is the solid-fluid interaction, and the chemical potential, which are dependent on the distance r. By minimizing the grand potential, the local density rho can be calculated at each possible distance from the pore wall, and we can finally have the density profile at the equilibrium conditions. Here is an example of modeling of the fluid density calculated for argon at 87 Kelvin on graphite. The bottom graph shows the gas to solid external potential of argon interacting with graphite. The distance from the surface is expressed in the molecular unit Z over sigma, where sigma is the diameter of the atom of the gas. It has the minimum at 1 molecular unit away from the surface, which means the gas atom favorably absorbs and sits on the surface of the solid. The upper graph shows the calculated density profile for this external potential. And at the low pressure, we see one peak at 1 molecular unit away from the surface. And as we increase the pressure, we have the first peak larger, and then we have the second peak, which represents the second layer of absorption. As the pressure goes up further, multi-layer absorption can be seen. Here is an example of the density profile of a slit pore. Since we have two parallel walls, we can see the two minima in the external potential graph shown on the bottom left. On the top left, we have the density profile calculated for each relative pressure. We can see that the density profile at low relative pressure, the density peaks correspond to the two minima shown on the external potential graph. The graph shown in the middle, labeled as the theoretical NLDFT isotherm, plots the calculated density shown in the density profile graph on the left against the corresponding relative pressure. So the first blue data point on the isotherm represents the first density profile shown in the top left graph, and then the second point represents the next density profile, so on and so forth. So as the pressure increases, we can see the multi-layer absorption happening within the pore, and at certain pressure, we can see those peaks starting to merge into each other, which represents the capillary condensation, and this can also be seen in the theoretical isotherm with this sudden jump. So in this way, the theoretical isotherm for the slit-shaped pore is calculated for each possible pore size, such as 0.4, 0.5, 0.6 nanometers, and so on. And in this manner, we have a family of theoretical isotherms, and this is called the kernel. When it comes to fitting the experimental isotherm, we can deconvolute this given isotherm based on the library of model isotherms that were calculated for the same analysis conditions, material, and the pore geometry. And then we can go through the process of regularization to finally obtain the pore size distribution. Here is how the NLDFT data reduction looks like on the MicroActive software. So we can choose the model based on the analysis conditions and the geometry of the pore. And we can select the regularization where both the RMS area fit and the roughness of the distribution curves are minimized. Another feature worth mentioning of the NLDFT method is the capability of merging two different isotherms collected with different adsorptive gas. This dual model is developed for carbons, and this becomes particularly useful when the sample takes too long to equilibrate when collecting nitrogen isotherm at 77 Kelvin at the very low pressure region, or when the instrument doesn't have the capability of collecting the low pressure data. If either of these is the case, the dual NLDFT model can merge the CO2 and nitrogen isotherms to get the comprehensive pore size distribution from micropore to mesopore range. On the far right, we have an overlay of the pore size distribution obtained from the dual model using the full nitrogen data versus the short nitrogen data, and we can see that they are very comparable. Here is how the dual NLDFT looks like on the MicroActive software collected on the TriStar. By overlaying the CO2 isotherm, we can characterize the pores under 2 nanometers. Thank you for joining me today. If you want to learn more about physisorption theory or upcoming training courses, visit micromeritics.com.